Welcome to Biomaterials. What are we going to talk about today? Today we're going to talk about a few methods for cross-linking. And in particular, I'm going to talk about covalent methods for forming covalent crosslinks. So, why might we want to form crosslinks? Well, if you go back to the lecture on viscoelasticity, the presence of particularly covalent crosslinks prevents those polymer chains from sort of slowly slipping past one another indefinitely. So, whereas something like polyethylene, if it's not cross-linked, those polymer chains, if you know, they last long enough for you to take your groceries in from the car. But if you put too much weight in that polyethylene bag, eventually it's just going to creep and creep and creep and creep and creep, and it won't really support appreciable load indefinitely. So you might say, hey, how can I improve some of the mechanical properties of some of these things? For example, by cross-linking. So eventually we'll get to methods for cross-linking polyethylene, but I'm almost going to pursue some of this thing in a chronological order. So no outline today. This is going to be a pretty quick lecture. So the first method that I'm basically going to talk about for forming covalent crosslinks is for a polymer called cis polyisoprene. And you might know this by its more common name as latex. So latex shows up all over the place, right? It's the rubber that makes up our balloons. Um, it's the rubber that makes up many types of rubber bands, right? Not very stiff, pretty stretchy, large strain to failure, but not a pretty, but this piece of rubber I can break with my hands. Not a super strong material. So, what does this look like? Well, here's the monomer. No, that's not a drawing of a horse. That's the carbon, 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 carbon. Rest of it's occupied by hydrogens, except for these double bonds right here. So what process would you use to polymerize this monomer? Well, anytime you see carbon-carbon double bonds, you might think that radical polymerization is basically the way to go. Turns out that radical polymerization for this one is actually a little bit tricky. Basically, the radical attacks this one, pushes the double bond up here. This double bond then basically pulls one of the electrons up here and pulls the radical over here. But you basically end up with something that looks like this when you polymerize it. And until that radical has basically found something else, either found some other chain to halt the polymerization, this is basically what the repeat unit looks like. And in contrast to other polymers that we've seen in the past, this molecule is pretty interesting in that there's a double bond in the backbone. We contrast this to, for example, polyethylene, where basically, there were double bonds in the monomers, but sort of all the double bonds got cracked open and used up when you formed the polymer chain. So the key thing here is there's a double bond in the backbone, and it turns out that this is an opportunity to create crosslinks. Basically, crosslinks can form by sort of opening up this double bond and using sort of some of the free slots on the adjacent carbons to form bonds with neighbors. Basically, here's where the cross-linking can occur. Why might we care about cross-linking cis polyisoprene, right? Well, it turns out that latex, by itself has pretty poor mechanical properties, right? Like these rubber bands, I can just break them. Rubber gloves, rubber balloons, not a super strong material here. But latex was actually one of the first polymers that was um, that was improved in its mechanical properties through an artificial process. And it turns out that latex mechanical properties are basically improved via a process called vulcanization. No, not this kind of vulcanization. Live long and prosper indeed. But and this process of vulcanization is basically heating this polymer. It's already polymerized, but it's basically heating this in the presence of elemental sulfur. What happens when you do that? Basically, the sulfur creates covalent crosslinks. By disulfide bonds. So what does this look like here? Well, you can sort of imagine there might be one polymer chain that looks like this. And sort of at one site, the double bond was sort of cracked open, and you might have some number of sulfur atoms covalently bonded to one another that then these sulfur bonds combine with an adjacent chain. So basically what happens here is these sulfur bonds can sort of crack open, the sulfur atoms in the presence of heat can crack open part of the chain. Most of the chain remains intact with sort of still a covalently bound backbone right here, but there also basically creates these covalent bridges between here. And it turns out that, depending on exactly the temperature and times and concentrations that you use in the vulcanization process, this can be somewhere between 1 and 8 sulfur atoms that participate in this bridge. What does vulcanization do? Well, so rubber prior to the vulcanization process is like cheap rubber bands. Stretchy, but definitely not super strong. After after vulcanization, think like the rubber in your car tires. Let me just take a moment now to describe what of a fanboy I am of the rubber that makes up in your car tires. So car tires go something like between 40 and 60,000 miles. And if you think about it, every time that wheel goes around, that's basically taking that rubber and putting it under a stress cycle. So when we think about fatigue, you know, it goes through an incredible number of cycles, right? If it's going 60,000 miles, think of how many times the wheel needs to go around in a mile, right? So these rubber tires need to last in the tens of or maybe even hundreds of millions of stress cycles every time the wheel goes around. They get stretched a little bit. Um, so they're lasting, millions upon millions of cycles, of stress cycles. They need to last in corrosive environments, right? Like if you go out in the winter, there's tons of road salt. It's wet. There's all sorts of, nasty things in the mud and in the water and in the air. There's biological attacks on them. They're left out in the sun, so they're constantly exposed to solar radiation. They're exposed to extreme cold, tens of degrees below zero, C or F, it doesn't matter. It's still super cold. And they're also exposed to, you know, um, like 40 degrees C or, over 100 degrees F, depending on where you live. While undergoing all of these things here. Think of what an amazing material that is, right? That needs to survive in such a harsh environment. And and how does it able to do it? Like, no way a rubber band would be able to withstand all that abuse. Let's hear it for vulcanization. This is amazing. So this is the type of radical change. Radical change. No, no, no. This is the type of radical change that a material can experience once you cross-link it, right? These amazing mechanical properties. So going back to here, I said that these sulfur bridges can be somewhere between 1 and 8 atoms. So let's think about two applications where we might want vulcanized rubber. Let's say we want it to withstand high temps. And then let's say maybe say in some different application, we want it to withstand lots of stress cycles. So for which of these, so take a moment now, pause and ponder. Pause and ponder, for which of these cases would you want a large number? Would you want a long bridge? And which of these cases would you want a short bridge? So pause and ponder. Which is best for a long bridge? And which is best for a short bridge? In terms of the number of sulfur atoms that make it up. Well, which one's best for a long bridge? Well, if you think about lots of stress cycles being applied to these chains, every stress cycle I'm stretching these out and letting them go and stretching them out and letting them go and stretching them out and letting them go. It would be nice if these cross links could support some of that deformation without actually fully straining and breaking the bonds between these chains. So if I want this thing to support, to be able to withstand large deformations, then I want a long bridge between them, because basically a long bridge gives flexibility. A long bridge gives flexibility, which allows the thing to support a large number of stress cycles. And then I guess by process of elimination, a shorter bridge is better at high temperatures, but let's think about the physical rationale here. At higher temperatures, it turns out that these sulfur-sulfur bonds are sort of more vulnerable to thermal degradation. If we kind of picture these things all sort of bumbling around, the sulfur-sulfur bonds are the ones that are vulnerable to degradation at high temps. So basically having a fewer number of those and sort of, having the sulfurs directly bonded to the carbon ends up being a more secure bond, right? So basically the sulfur carbon is more stable, so fewer sulfur-sulfur bonds is better at high temperature. So that's the rationale there. So what's the key thing here? Well, this is just one way that that cross-linking, and in particular covalent cross-linking, um, makes our lives better, right? Gives us polymers with incredible mechanical properties. In the context of biomaterials, how often do we use vulcanized rubber? Well, it turns out that the body mounts a pretty huge immune response, in response to latex. Basically, people have allergies to latex, and even people without specific latex allergies generally upon implantation, particularly for vulcanized rubber, like there's no way that this avoids some kind of catastrophic immune response. So for biomaterials, well, we can certainly use this for things like latex gloves, and we can certainly use this for applications like car tires that sort of need to withstand sort of intense mechanical stress. But in terms of like implants and stuff, not very good for implants. Neither is good for implants. And that's primarily due to the immune response. And we'll get into the detail, and later in this class, we'll get into the details of exactly what makes certain materials, good or bad in terms of eliciting inflammation in the immune response. So, under what circumstances might we, might we cross-link? Might we think about cross-linking materials in, for implantations? Well, let's think about two materials that that could potentially be used. So we talked about high density polyethylene, which if you remember was just a hydrocarbon chain, and it got most of its strength from the weak but numerous chain-chain interactions, right? These van der Waals attractions between the chains here. It turns out that there's a material called ultra-high molecular weight polyethylene, ultra-high molecular weight polyethylene. And it turns out that ultra-high molecular weight polyethylene is the same as this, just longer. It's even longer than high-density polyethylene. So basically, you get those chains so long that you almost never have any dead space. Almost never have any dead space between, between chains when the chains ends, because they end so rarely that you basically you have really strong interactions between all these chains. It turns out, but ultra-high molecular weight polyethylene still suffers from this problem of creep, where if you apply forces to ultra-high molecular weight polyethylene, it's still only they're very numerous, but still very weak bonds that form those chains, and eventually they can slip and slide past one another and they creep. So ultra-high molecular weight polyethylene, has its uses in implantations, so useful for implants. And in particular, one type of implant is the wear surface for knee implants. Right, for knee replacements, basically you can have these plastic surfaces wearing upon one another. They're pretty smooth, right, and pretty low friction, but eventually they do wear out. Now, one thing you can do is, right, and they basically wear out because eventually these polymer chains sort of slide past one another and degrade. So it turns out that one improvement you can make upon high-density polyethylene, or maybe even ultra-high molecular weight polyethylene, is to cross-link the chains. And what would cross-linking the chains do? Well, generally it would sort of increase the strength and stiffness and it would basically prevent long-term creep. It would prevent long-term viscoelastic creep, or I guess this might be viscoplastic creep, because the deformation would be permanent, but it would basically prevent this sort of long-term deformation of the material here if we could cross-link the chains. Now, unlike cis polyisoprene, polyethylene doesn't have these double bonds which can sort of be popped open and accessed for forming sulfur bridges. Instead, the way that you cross-link polyethylene is by stealing off some of the hydrogens through a radical process. So the way you cross-link, so cross-linked polyethylene has a special name. It's called PEX, where the X stands for cross-linked and the PE is polyethylene. And you might have experienced PEX in tubing or pipes for your house. Basically, most people's homes have copper pipes to supply water, but it turns out, copper is pretty expensive. Um, Basically, cross-linked polyethylene, those tubes that carry water to your house, hot and cold or whatever, they're constantly under pressure. So, polyethylene just by itself would not be a great material because eventually those tubes would sort of stretch out due to that constantly applied pressure, and then they would leak at the seams. They would leak where you sort of joined them together after they stretched out a bit, but cross-linked polyethylene can prevent that stretch under pressure. So PEX tubing is actually, pretty good um, at at um, is pretty good at resisting that long-term deformation. So basically the cross links in the polyethylene prevent those tubes from stretching out and eventually leaking and, flooding your house or whatever. So newer construction homes might have PEX tubing instead of copper. It's cheaper and, due to its sort of mechanical properties, fits the job. How do you actually form PEX? Well, you basically have one polymer chain, and let's imagine that this polymer chain, has its hydrogens on it, and then let's say there's some adjacent chain that has its hydrogens on it, right? And all of these carbons would be fully saturated with hydrogens. Well, it turns out what you can do is you can basically have this plus a radical initiator. So if you remember, these radical initiators basically had some molecule or some molecular motif, I'll call it R, and they might have an oxygen single bond, and then another R right here. And what happens, you basically have the polyethylene, you embed a little bit of extra um, radical initiator right here, and then you basically use something to crack open this oxygen single bond, so light or heat, to basically crack open this radical initiator. If you remember this radical, the way this radical initiator works is it is light or heat or whatever breaks this oxygen single bond and replaces it. And essentially by breaking this bond, you sort of create two free electrons that are, kind of free to do whatever they want. These electrons basically switch places with adjacent hydrogens. So by cracking open this radical initiator, you basically create two radicals right next to one another. Sometimes those radicals just recombine with each other, but other times those radicals go and attack the hydrogens, replacing the hydrogens and sort of swapping places with them right here. So after you apply lighter heat, what do you end up with? You end up with something that looks like this. We have a chain with a hydrogen right here, and then one of the freed electrons that came from one radical, an adjacent chain right here, one of the hydrogens here, and then the other radical that came from this one. The radicals are then left with R, O, and the hydrogens that came from them. So we have two R, O, H's. And then, well, what do you get right here? These then form a single covalent bond. And then basically, as long as you have some way to then leach out, whatever this junk was left in here, you can basically form polyethylene that is essentially as dense as it was originally, but instead of just having some hydrogens weakly attracting one another periodically, instead you get actual covalent bonds bonding adjacent chains. So you get covalent bonds not only along the chains, but covalent bonds across the chains as well. And that's what gives PEX these incredible mechanical properties. So basically, you form these crosslinks, you increase the strength and stiffness even beyond what polyethylene has normally. You prevent long-term viscoelastic creep. Of course, the downside is that you generally make this material just a little more brittle than you would have otherwise, right? You basically have these covalent bonds between here, so basically you can't deform these chains too much without trying to tear open that uh, breaking that covalent bond basically results in kind of a brittle catastrophic failure. So unfortunately, when you do this, you increase the strength and stiffness. That's great. You prevent long-term viscoelastic creep. That's great. But you also make it brittle, make it at least a little more brittle. Again, not so brittle that it's disastrous to its mechanical properties. PEX can basically still withstand water freezing within the pipes without the pipes cracking. So don't get me wrong, PEX is still pretty compliant, but it's definitely more brittle than the original polyethylene was. So it makes it more brittle than the original high density polyethylene, but still pretty compliant. Still pretty tough material. So 3 cheers for PEX. All right, so I think that does it for today's sort of little mini lecture. Thanks again for watching, and good luck with your study of biomaterials.